We'll just get started. And last time we talked about some generative model. Actually, we finished up RNN. I talked about echo state laterals, and then we start talking about generative models. And I kind of went through a little bit GANs, but we also talk about pixel CNN and pixel RNN. I probably repeat a little bit about GANs today, since I don't think I'm happy with what I did last time. So let me just move to the slide there. So again, this is the block diagram for GANs. So it was invented by a good fellow, when I believe he was still a PhD student then, in Montreal. His advisor was Benjio. And so the idea is basically you told her, hey, Jihao, can you hear us? Okay, so he can. So I guess he's trying to set it up. So the idea is basically you want to generate data. So, but what we are trying to do is we're trying to use a game theoretical setup, not exactly theoretical, but game setup, like two players game setup, a non-cooperative game. So you have a generator that's trying to check the discriminator. Let me change to wet here. So trying to check a discriminator. So basically, discriminator will get sample both from just the true sample, ground truth, maybe trying to discriminate some handwritings of someone that they have some true samples there, and then the generator will try to generate some samples, just trying to imitate that data sample, the true data sample, as much as possible, trying to check this discriminator. And then this discriminator, of course, needs to try to distinguish which is true, which is false. So, and this is a little bit more I would say detail in terms of notation. So, for the generator, basically accept just a C. It's like a random number, and then based on C, we're going to generate a sample. So it has and again, then there's a ground truth there. We'll assume the distribution is given by Qx here. So then the discriminator basically need to figure out whether this x is from the distribution Qx or from something else, and it will give out a score. That score basically is saying more or less what's the probability that, or the belief that that x belongs to the original, that is genuine, basically. And then as I mentioned, it's a Minimax game. Basically, it's just a two-player non-cooperative game. So you have two objective from two sides there. So and for the model is basically from the generator. Basically, it will have some input distribution for the z there, and then for each input z, it will kind of have a conditional probability, conditional distribution to generate the x, right? So the PX model x is pretty simple. I integrate over all z there, and the ground truth is based on just Qx here. And the discriminator will want to catch the data based on the cost function here. So you have the discriminator. Okay, dx is what the score output from the discriminator, right? So if you look at this is essentially just the cost entropy for taking d as the classifier, right? So if I have the true label, it's okay, the input is from the p data, then supposingly that if he's doing okay, then he should verify that all of this should be 1, then this value will be equal to 0, then the cost will be 0. And on the other hand, if the input is actually input to this discriminator is false, is fake, then it should figure out this is like, DGC should be 0. You're saying that, okay, the discriminator will believe that the input is false, therefore it's not genuine, it's fake, so therefore it's output 0. So then again this will give us 0. So in any case, this basically is just a cost function evaluated using a cost entropy loss, and this will be the discriminator loss, right? And it try to minimize this as much as possible in the view of the discriminator. And then in terms of the generator, it will try to trick the discriminator as much as possible, right? So therefore, its cost should be just opposite, right? If you, in terms of both players trying to minimize the cost, then the generator cost can simply define as the negative JD, minus JD here. And of course, if you think of the generator, if you look at these two terms here, the first term does not really depend on G, right? So it has no control for the generator, so therefore we basically can ignore this term here. So therefore, we may write JG, the cost of the generator, simply as this one. So now we may try to optimize this discriminator function. So find the dx here with respect to this cost function here. So therefore, we basically we're just trying to find the optimum, right? Optimum dx there, and because x itself, dx itself is a function, we cannot just take derivative and so on. So we need to use calculus of variation. So assume that d star x is the optimum, and let's say delta x is any arbitrary function. Then this thing, if I take derivative with respect to lambda, should goes to 0 as long as lambda goes to 0. So basically saying that no matter how I vary this delta, if I have this, essentially saying that tiny perturbation to dx, d star x should basically the cost function should be 0, right? So that's basically this. If you think of that's exactly analogous to taking minimum or extremum of a function, that if I take a tiny perturbation away from the extremum, so that's still the slope should be 0. So basically that. So now if I take the derivative for that, then so this is pretty simple because JD is just log function there, two log function term there, and then it's expectation log function, but I can take the derivative. Derivative can go inside the expectation. Then log function is just 1 over these two guys here, and then this expectation I can rewrite it as okay. First of all, delta lambda should go to 0, right? So these two terms can be ignored, and then this expectation I can write it as this function times p this data and take derivative, right? So therefore I can rewrite this two terms here as this one here. Now this one is equal to 0 for any for basically any delta, or this is equal to 0 for anything. So therefore we should have this thing is equal to 0. Therefore this will give us d star x is equal to this thing here. So that's the optimum discriminator, and this typically is quite reasonable, and as long as if you have a good estimate of p data and p model, we can just take this. But in terms of the generator, as we mentioned earlier, that we can pick the generator cost function just as minus this guy, or maybe just equal to this guy here. Just ignore the first term there. This is intuitive, but the problem is if you think of that, the generator, what it's trying to do is to minimize this cost, right? So when the generator first start creating some kind of fake data there, most likely it's not able to fool the discriminator. And when it's not going to able to fool the discriminator, it means that basically dgc will be approximately equal to 0, right? Remember that d is the discriminator, D will say this is genuine. If it's, then it will say it's 1 if it's genuine. If the input is fake, then it will output 0, right? So if the generator is not able to fool the discriminator, then this means that this one will be approximately equal to 0, right? And so therefore, like this term here, log 1, approximately log 1 will be approximately equal to 0. And basically, and also at that point, like log 1 plus x, right, when x is very small, the slope is pretty small. So therefore, it's not good to try to optimize the cost function there. So instead, we can just typically we'll use a surrogate of this one. Instead of like expectation this log 1 minus d, we will say like minus expectation log d here. Now if you look at this guy here, when dg is approximately equal to 1, that's basically saying that like the generator is able to successfully fool the discriminator in that case. Then we'll basically ignore this cost, right? For this particular case, we will ignore this cost. And but if like generator, if DGC is approximately 0, saying that like the generator is not able to fool the discriminator, then this value will be much bigger than 0. So basically we'll focus on the sample or the output sample from the generator. The generator will focus on the samples that is not able to fool the discriminator at the beginning. I mean, it makes sense because if you imagine that you have discriminator and generator just started to train, most of the time the generator, of course if the discriminator is pretty stupid, but if the discriminator is reasonably doing a good job, then the generator should have a hard time fooling it, right? So therefore, like it probably most likely will in this region here. So therefore, it's good to use this surrogate cost function instead of this one, the original one. But of course, like if you in the region that like the generator is able to fool the discriminator most of the time, that means like around here, then in this case, like it becomes like this cost function will have a pretty flat slope in that case. Then maybe we want to switch back to the other one. But of course, like in that case, you may want to ask another question, whether this discriminator is not doing a very good job, really, that the generator can fool it easily. Maybe you should train the discriminator better. And this you can ignore this. I just want to illustrate this figure essentially. That's the basically this is the original cost function, generator function, cost function for the generator. So in this region, as you can see, like that, the slope is pretty flat. That's when like basically the discriminator is able to discriminate basically everything generated by the generator. I mean, to figure out that those data are all fake. Then in that region, you probably want to use this surrogate like cost function instead. And as I mentioned, on the other extreme, you probably want to switch back to the original cost function. And there are quite a few refinements for GAN, because if you think of GAN, I'm not sure like how you guys familiar with game theory, so latch equilibrium and so on. So you have two players, one doing a long cooperative game, and latch is also, of course, very famous for proving that like there's always have a latch equilibrium there. But the proof is like something again like this is kind of one of those long constructive proof. It's saying that the equilibrium exists, but most of this two-player long cooperative game is very hard to find the latch equilibrium. So it's the same for this here, like for the GANs also. So therefore, like there's quite a lot of work actually since 2014 is like how to better do some refinement to better find the latch equilibrium there. So I'll just like look into a couple of them, just mention a couple of them. You may want to also check in this paper by Salimans. It's pretty well written paper and have lots of other ideas as well. So first, I'll just mention this one-sided label smoothing. As I mentioned, like the cost function, the original cost function for the discriminator, you can think of like, okay, this is a little bit hand-waving way of writing this thing, but it's just simplified. So, but you may need to go back and write it yourself, like precisely what it is. But it's essentially it's like doing a cross entropy between one and also a basically a delta function and also a discriminator data, and then plus this other way one. So this is like from the original data, I mean the genuine data, and this is from the fake data basically. And then like some experiments shows that like we can get better stability, enhance the system stability if we kind of smooth the this cost function a little bit, in the sense that instead of like making very much confidence saying that the label for the true labels, the label is exactly is true, but instead we'll say like actually it's 0.9 probability that like that data is true, something like that. So basically you have the training data here, the data you know that it is genuine data, but we'll still lower the confidence there, saying that okay, actually I would say it's actually 90% genuine. And we do that is that in the sense that it will prevent some extreme samples, because even though you have genuine samples, but some of the samples may look kind of extreme. Maybe like you have someone like, okay, it's genuine. For example, if you have a signature recognition, my signatures every time is different, and some of them probably look a lot like fake data. So you may want to like lower the confidence sometimes. So and of course you may be interested why I don't do for the other way one. Maybe you want to put 0.1 here also, but it turns out that if you also lower the confidence for the fake data, so in the sense that the data fake, but you say okay, I don't think it's really fake, and then you end up have a problem basically that you can derive the optimum discriminator will be something like this. So will be, you remember the original is like this way. So alpha is equal to 0, beta equal to 0 is like this. But now if I have alpha and beta is non-zero, in general it's something like this. And the problem is if you have a beta here, that tends to give you some undesirable bias to the data generated by the generator. So because it's hard to explain. Just maybe you want to go into the paper like to. I probably will say more things that say something wrong. So, but anyway, you can check out Salimans' paper for his reason. Another refinement I already mentioned last time is that like other training, we tend to use batch normalization, right? But in this case, if you use batch normalization, the batch tends to have like strong influence to your final model. So, for example, like this is like the generative model trained by like 2 different batches, and apparently you can see that it have a great influence to, I mean, the coloring of the data here, and so this can kind of mitigate a little bit using so-called reference batch. Basically, it's just like you select one particular batch and saying that I'm going to normalize all other batch data using the same reference here. Basically, like all the mean of the variance will be computed using this reference batch, and then normalize all the other batch using this means and variance. And we also mentioned that this virtual batch norm is just a mix, so we will kind of normalize with both the mean and variance, basically mix the current batch with the reference batch, and then compute the mean and variance, and then normalize the current batch. And so another thing like I like to mention is like we want to be careful about like balancing G and D. In many cases, it's preferred to have like a bigger and deeper D. I mean, in the sense that you want to have a smarter discriminator. So if your discriminator is bad, then basically the generator will just generate like trash. And and therefore, like, besides a stronger model, there's also some research that will try to have like more D-step iteration than G-step iteration. Yeah, I already mentioned that like there's some labels moving, okay, let me give an example here to say like why that D is supposed to be smart. This is like an example like okay, I will assume both discriminator and generator use the same cost function, therefore it's exactly a Minimax problem here. And note that like for a Minimax problem, like mean mass is not the same as mass mean. In general, they don't have the same solution. And in particular, for training this particular distribution, basically like you want to train the model such that the model will have a distribution like this. So this distribution have multiple modes here, right? So have 8 modes there. And in terms of like whether you put the discriminator or generator in the inner loop, you have totally different results. So for example, if you take the discriminator in the inner loop, so that means that you do more iteration for the discriminator, you will end up have a correct distribution. But if you put the generator in the inner loop, you will end up just learning the modes, like this case here, and this won't be quite desirable in most applications. And this is so-called the mode collapse problem. And one kind of like workaround for this one is to reduce the mode collapse. It's simply when you generate the data, you can introduce so-called some mini batch features. So basically, like, so you generate some data, you classify whether like your sample generated is already included like by your model. So for example, you already have a model like kind of trained in the sense that the generator created samples with something like close to here, and therefore have some particular features there. And now like you keep training the model, and then like try to look into like what kind of like data is generated, and want to see like whether the newly generated data will be similar to the previous one. If it's so, then we will just like disregard this new update. So then we're trying to reject sample when the features is too close to the existing one. Too close, yeah. And another workaround is by Google Brain. So they try to kind of like make sure that like it's going to solve a mean mass rather than mass mean problem. So it's quite simple. Basically, you just force that your discriminator in the inner loop. So you will unroll k future steps and predict what the discriminator think. So and because like the generator is doing the unrolling, the generator is actually in the outer loop, the discriminator is the inner loop. So therefore you can make sure that the solution is like an approximation of a mean mass problem rather than a mass mean problem. And this is like the results kind of like after for example 25k epochs, then you can approximate this pretty well. And now let me talk a little bit about this not exactly extension, but just application, like in particular combining GANs with like conflat. So there's a work called DC GAN like by Webford like in 2016. It's essentially just like a conflat combined with GAN, and it has so both the discriminator and generator again are conflat, and I think they replace all the polling layer with dried convolution, so old-fashioned dried convolution. So therefore, it's a fully connected conflat, and it use batch lom and use value, stuff like that. You can get into detail like if you're interested. So, but the results is very interesting. Like this is like they test it on the so-called Elsun dataset. It's like dataset like with bedrooms, and I guess it's like indoor scene. So, and this is the artificially generated image basically, but many of them looks quite real. Of course, it's a kind of low resolution. Like this guy look, yeah. So and also like you can fine tune like, because I remember GANs like there's an input vector z there at the beginning in the generative models, and that z vector like potentially like for all different z values will correspond to something. So then actually you can interpolate like between two random values. For example, like if you have one image, you know that it's generated from one z there, then other is generated by another z there. Then you can interpolate between these two z values to get a banding kind of image, like band between like one extreme to another extreme. And these z values can be kind of interpretable. Like you can do like mathematical, just arithmetic there also. For example, like you have this, it's basically you have a z average value, like this is all smiling woman, and maybe you have different z value there, like train z values there, and you take the average of the average vector, and then you have a neutral woman value, and you add all together. Then and similarly, you can have a neutral man here. Then when you subtract a smiling woman from a neutral woman and add back a neutral man, then you can get like some smiling man face. And you have other kind of interesting manipulation also. For example, you have like man with glasses, subtract man without glasses, and then like add back woman without glasses, then you will have like woman with glasses. Yeah. So and that's the one I just mentioned is like the DC GAN is kind of low resolution, but almost immediately another group like trying to just make two-stage kind of generators. Basically, one generator, they have one generator just do a sketch, like get a low resolution image, and then use that to try to combine with another GAN stage and then create a higher resolution image. And the result is pretty amazing. Basically, it can generate images like quite high resolution from a test description. For example, here like a white bird like with black crown and yellow beak, and you can generate this kind of image here. This is the first stage here, and the second stage you get much more high quality images. And there's more results here, like the flower is white, pink, and yellow in color, and has petals like multicolor, etc., etc. This is another application, but I don't have. I tried this last year, but I didn't have it now. I need to put on my GPU laptop to try that because it takes lots of computational power. So it's trying to sketch something that automatically generate some image. Basically, like last year, just a year of GANs, like lots of applications there. For example, this one is pretty interesting. You do automatic coloring, and of course, it does also work trying to make scans stable, as I mentioned. And that's again a zoo that. If you're interested, you can check out the links there. So there's some pros and cons for GANs. Like, of course, now it's very popular at this moment, and probably still quite will be quite popular for the next couple of years, maybe until people find new toys and move to another area. And basically, the idea is very simple, state of the art, but it's kind of unstable to train. And in any case, it's like it's still like a very active research area, as I mentioned, and there's lots of techniques has been introduced trying to stabilize GAN, like this versus GAN and like LS GAN and many others, and and also like apparently there's lots of applications, as I just mentioned. Actually, I'm not going to run a kind of I would just like to show you a DC GAN implementation, for example, because let's see, like actually. Yeah, this is a demonstration of like after each epoch, like how efficient GAN is trying to this is trying to train for the endless data set, so it's able to generate more and more like true handwritten digits, and that's the kind of the cost function it generated. So it's hard to see like the values. I guess probably the scale problem, I assume it's like going down for the discriminator loss, but the generator loss. So as the discriminator getting better and better, of course the generator has hard time also trying to catch up. Yeah, this is basically the same thing. But if you look at the source code, actually. Actually, maybe I want to make it bigger so that you guys can see it. For example, look at the train program here. It is quite short, like 114 lines. Of course, this does not include the models. It's put 2 of them. So this is one of the DC GAN implementation I find online. So if you look at, let's see. Oh, by the way, this is by they are using PyTorch for this one. So the main loop here is quite easy to understand. As you can see, like you have basically the training for the discriminator for the real data, and also the fake data here, and then you train the generator. And in the case, basically the criteria is the cross entropy, and he's not using the update as I mean the surrogate cost function for the generator as I mentioned. He's basically using the same I think so. It's basically using this same just 1 minus the. No, maybe he does use it, but it doesn't matter anyway. So I would just say if you're interested, just go online, because I just search. I didn't even like look for any kind of packages implementation. I just focus on PyTorch because I'm most interested in that package. And even for that, like if you search PyTorch DC GAN, like there's more than like 4 or 5 implementations there, and some of them are pretty short, like this one. And you can start from there and already modify something and play around with that. And let me go back to my slides here. So what I'm going to talk about next, I like to talk about autoencoders, and actually more precisely because I talk about it here because one of the other popular generative models is like variational autoencoders. And of course, before we talk about variational autoencoders, it makes sense to talk a little bit about autoencoders. So actually, this is one of the breakthrough there. This is this is included in the 2006 paper, Jeffrey Hinton's paper, that basically showing that you can use neural networks to do a much better dimensional reduction, dimension reduction than like plain PCA, and that's actually one of these milestones that got everyone excited and get into the neural networks area again, basically again okay, we talk a lot about dimension reduction. There's some PCA here. I'm not going to go through this again. But all you guys should be aware that PCA is kind of optimum. Okay, what maybe just a 2 minutes introduction again. PCA is basically just trying to find the principal components, right? So you have data point as a distributions. You want to find in which axis that the data have largest variance, larger scattering. So then it just goes through one. Of course, intuitively you can think of going one axis at a time, but in practice you can just decompose the whole thing with SVD, single value decomposition, and then you can get the whole thing there. And PCA is kind of optimum in the sense if you have a data cloud there, you want to trying to reduce the dimension. As long as it's a Gaussian-like, if the data cloud, then PCA is optimum. But of course, if your data is more or less for example, in high dimension, maybe what's called Swiss world or something like linearly distributed, then PCA won't be optimum. And and of course, you can implement PCA with SVD, as I mentioned, and SVD is just basically decompose any matrix into 3 matrices, right? 2 of them are basically orthonormal matrices, contain orthonormal vectors, and then the middle one is just a diagonal vectors. So it has some nice geometric interpretation for SVD, because if you think of the original matrix is some linear transform, then SVD is basically saying that any linear transform can be decomposed as first rotation and then scaling and then rotation again. So that's about it. So if we assume that of course this is not a math class, we just assume that every matrix has a SVD decomposition, and it does really. So then when think of you have a covariance matrix of some data points here, you have X is all the data points, or more precisely, X is basically the matrix that contain each column is the data vectors here. So each column is a data point. So then approximately the covariance matrix will be just X transpose, right? Or if you want to be more precise, it will be over K to normalize that. Then I can decompose C with SVD, right? So if I decompose C using SVD, I have that. Then immediately what I can see is that I'm not decomposing C. I'm decomposing X. I decompose X with SVD. Then my C can write it this way, right? Will be proportional to this guy here. Then because my V and U are basically orthonormal matrices, and of course this is transpose here. This will get the transpose. This guy should get me V sigma U transpose here. Remember, sigma is a diagonal matrix, and V and U are orthonormal matrices. So therefore, V transpose V will be an identity matrix, because every orthonormal matrix you multiply with its transpose will get your identity matrix. So this go away. So I basically will just have this. So therefore, basically, the eigenvalues of C will be just the singular values of the or like the single values will be just the square root of the eigenvalues. Let me be more precise. The single values of X will be just the square root of eigenvalues of C. So, because the PCA in effect is just keeping the m largest eigenvalues, right? So therefore we can immediately get those eigenvalues from, or like the eigenvectors, or eigenvalues of the corresponding eigenvectors from the singular value decomposition of X. And there's a proof for that. I guess I won't go into detail. But yeah, it's actually just a couple of lines. So in the sense that if if we have like X hat is as similar decomposition of X, but with like basically sigma hat here, it's only keeping the m largest singular values there. So meaning that like our original sigma is like this. It's diagonal matrix, right? I may sort these single values, maybe like it have like 9, 8, 7, 5, whatever, something like that. Now sigma hat is basically a truncation of like sigma. So I will basically this is sigma. I have sigma hat. Maybe it's just equal to 9 and 8, and then all 0 there. Then I have the corresponding X hat will be like U sigma hat V transpose. Then the error of X of this the difference that you can think of, the square difference of X hat from X will be just yeah, I can just write it this way, right? And then I can just replace it with a trace of a matrix is basically just sum of the diagonal values. So anyway, I shouldn't spend too much time on this trivial algebra here. I'll just skip this. But if you're interested, just look into that. So this I just showing that like okay, this will show that like keeping the largest eigenvalues will get you the PCA in the sense that like you get the optimum estimate of your X hat such that in terms of square differences, X hat will be closest to X. As long as we keep this, as long as we assume that we only keep a fixed amount of like components. And as we already mentioned, PCA is optimum in terms when it's linear. Actually, it's interesting to know also like as far as the decoder is linear, the optimum encoder is also PCA. So that is like if X hat, if I write, let's say X is the original input here, and X is like a reduced X here. There's like after some you can think of a compression, a dimension reduction of X here, and then I have a linear projection trying to recreate the original X. I have X hat equal to that. Then the optimum matrix is still this operation will be still a PCA. It will be still linear. Now the autoencoder, so it's essentially just trying to do the dimension reduction by basically building a neural network such that I start with the input, and I want to, after a while, recreate the original input here at the output. So it's like this one, and typically it has a kind of a, of course, because you want to do dimension reduction, right? So therefore, the middle layer you expect to have like a less number of hidden units there, and as we mentioned, so assume that like, okay, let's say I have here here. Let's say we have, okay, yeah, we have the model, like the typical models here, like neural network models. I have just x will multiply by the weight w and add on some bias, and the activation function here, I will just use sigmoid, and afterward, I'll reconstruct that linearly using a, let's say, a regression, linear regression. And note that, like, if I use linear regression, then in this case, this part will be optimum if we use a PCA, even though we introduce a sigmoid here. But it turns out this will be redundant because like this, as we mentioned earlier, if your if your decoding step is a linear step, then the encoding step will basically optimum using linear projection also. The optimum linear projection will be simply PCA. But of course, if you have multiple layers, then it won't no longer be optimum for PCA. So, and that's the part is interesting. This is not new. This is like for a long period of time, people kind of thought of that. Even dated back in the 80s, people think of like, can we do like multi-layer kind of neural network such that we can do a dimension reduction? But it turns out it's just very difficult to do, and so therefore it took lots of time, like until 2006, as I mentioned. Like Jeffrey Hinton had a breakthrough there, and the paper was published in Science. And the approach they use is actually quite different from like what people use now, because like what they did then is they try to use a layer by layer RBM restricted Boltzmann machine to pre-train the weights. Basically, they take each of the layers as a restricted Boltzmann machine. Of course, we didn't talk about that yet. Maybe we'll talk about that. Maybe we won't. And then like afterward, they just pre-train this, and then after they pre-trained it, they use the weight and they put it there, and then like they just layer by layer, they treat it as a RBM and do that and have those pre-training weights. And afterward, they just do a regular backplot, like to fine-tune all the weights there. And that's how they did that. And the result is quite appealing. For example, like this is like using the deep autoencoder. This is back in 2006 now in the Science paper. So this is the original, this is the reconstruction. Comparing from PCA, they got much better reconstruction. It's interesting that the earlier, I mean, like the glasses is gone somehow. I guess those are the not important features. They also like tried different experiments. Like here, you have trying to kind of do a clustering for like different documents. Like I think they have like 400,000 like business documents. I'm trying to categorize that. Like of course you can do PCA, right? You can do clustering or like k-means. Or I should say like you can basically, the classic approach would be like, for example, you can if you want to visualize that, you can first like do PCA kind of like down, kind of reduce the dimension down to like 2D, and then use like k-means to like cluster the data. But you probably got all the mess. Like, I didn't include a comparison there. It will be all messy. But here, like they have a pretty nice clusters here. So this is like a GAN and yeah, all pretty nice cluster result. And they also at the in the initial work they also use this for like image retrieval. So they basically the same idea, right? So you kind of create after you kind of reduce the dimension, you can do, for example, k-means to cluster that, and then for each cluster, you look at, okay, you give one image as your input image. You just want to check which cluster is from, and then you pull out data from those clusters and you get results. It's pretty nice. And there's other way of pretraining besides using RBM. For example, like later on, like by Benjio group, like in Montreal, they use this so-called stack autoencoder. They kind of like they kind of they consider like a deep autoencoder as like a combination of like several shallow autoencoders, and then like each shallow autoencoder they're trying to train it, and it turns out it's easier to train than RBM, and that's some interesting work at that time. And there's some following work like along this line for autoencoder. For example, like there's some work like called denoising autoencoder. The idea is basically like we want to make sure the autoencoder is kind of robust to noise. Like you assume that you have this input X, like the data set may be noisy. Then what we may do is like if the data is kind of binary, we may kind of like randomly fit some bits to introduce some binary noise, or like if you have kind of like the input is like continuous, then you maybe add some Gaussian additive noise. So in either case, like this very simple idea, it just can make the representation, the eventual representation more robust to noise. A similar idea is also introduced like by, I think, the same group, if I remember correctly. They have this so-called contractive autoencoder. So this one, instead of, it's the same idea, you just want to have the models kind of more robust to sensitive to kind of slight changes like in the inputs. So what they did is basically, okay, imagine that like in each layers there, so I want each layer, or like actually I have layers here, so for each unit here will be less sensitive to the change of the inputs. So what they does like is like they want to force the weight, so the corresponding weights there, like because you have this here, like you want to force the corresponding weights here such that the gradient doesn't change that much with respect to the input. Of course, that will be like a little bit complicated in terms of math here. I won't go into detail. So essentially, it's just like you trying to introduce a regularization term in terms of the Frobenius norms of the gradient of those weights there. Actually, gradient of the change of those hidden units there with respect to the input. And some pros and cons there is kind of deterministic compared with the denoise autoencoder. And it's more stable also comparing with like denoising autoencoder, but you need to compute Jacobian for the hidden units, hidden layers, and also kind of more complex because like for denoising autoencoder, you add some noise in the input, right? So it's very easy. You just write 2 lines of code and you got it. But here you need to explicitly kind of change lots of stuff. So actually all the results I mentioned here, like up to 2011, they all use some like pretraining to apply to the weight, and then they use backpop. It's actually interesting, like to realize. Okay, I went through this very quickly for another reason. Is I think it's still useful knowledge, but it's a little bit out of fashion in the sense that like pretraining, like for many many researchers will kind of consider that as like not necessary anymore. So, and also like there's some disadvantage in pretraining. For example, this is a core reply by Benjio himself, like, and he said that like one disadvantage of the pretraining is that like it's greedy because like you take each of these two layers, either you use RBM or like the stack autoencoder pretraining. It's still like you use like 2 layers or 3 layers at a time, and then you look at stuff kind of locally and you try to optimize that. So therefore that's what he means by greedy. And then like so therefore like you got some weights there. It's easy to converge to your final result, but you start with some point like it's a little bit greedy at the beginning. So most likely you won't end up at global optimum. Of course, I don't know. It's a conjecture, I would say, because neurolecture, in any case, you have so many ways, it's hard to say like whether you get to global optimum or not. But there's also like interesting remark, another remark by Goodfellow. And Goodfellow, he was a student of Benjio also, and if you I don't know whether you check out the textbook. It's on the website. Okay, this is the textbook of the deep learning. And Goodfellow is the lead author for the textbook, and he's co-author with I forgot who's the second author. I think Benjio is the third author. And I'm also like you should realize that Goodfellow is actually introduced GAN. He's the inventor of GANs that we just mentioned earlier, and actually this is a call reply. I find it interesting. This is a discussion saying that like why people think the autoencoder is a failure. So and he said no. In the sense, it's just like autoencoders. I guess it's like some of other technologies. People have had lots of high hope on that, and then they realize that it seems that like it doesn't have as broad applications as they thought to be. Then people just, I mean, the expectation doesn't match with the result or something like that. But it still is very useful, as you see like earlier, like showing like the 2006 paper by Hinton. The autoencoder is still very powerful in terms of dimensional reduction. It's doing very good job there. Just like because many people are interested in recognition problem, like in machine learning. For example, you always have like computation problem. You want to recognize whether it's a dog or a cat or something like that. And people realize that like if you just want to do recognition problem,